Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff, the good stuff. This is the AAS Journal Author Series. And I am super happy to have Florian Peißker with us today. Hello, Florian.
Hello, Frank. How are you?
I am doing awesome on this November 6th of 2023 as we record this. And one reason I'm doing awesome is because it has finally cooled down a little bit in the desert here in Phoenix.
Oh, nice.
Yeah. So, we still get up into the, 30s by midday, but, it's
really?
quite pleasant.
Oh,
Yeah.
wow.
We're still quite warm
Oh,
in the
wow.
afternoons.
Yeah.
That's why we get so many snowbirds coming down from Canada.
Okay.
So I love those warm afternoons in
Yeah,
November,
sure.
December. So,
Yeah.
and how about you, Florian? Where are you located at?
So I'm right now in Cologne,
Cologne.
in Germany.
Okay.
So, and winter is knocking on the door. So here's chilling, and a little bit colder. So yeah, and right now I'm in my office.
Very cool. Very
Yeah.
nice. Very cool. And Florian, what do you like to do for research?
So my main research topic is the galactic center. So this is where I'm most of the time, looking at, but also a little bit cluster dynamics, galactic clusters, and yeah, lately it's a little bit broader, also because of my scientific portfolio, I would say, because of the James Webb Space Telescope
Oh,
launch.
yeah.
So yeah, so we have like many observations, and this is also really interesting what we're doing there.
Indeed. In fact, I was going to bring us to this very interesting article.
Yeah.
And let's go ahead and pull the article up. And there we go. And this one is an APJ article. It is open access. It's open access era, people. You can go grab a copy, go get one. The Evaporating Massive Embedded Stellar Cluster, IRS-13, close to Sag-A, star 1, detection of a rich population of dusty objects in the IRS-13 cluster. And Florian, take us away.
Okay, thank you. So first of all, I would like to thank my co-authors, namely here Michael Sayacek, and who like often contributes a theoretical point of view to my research, and so we are in close collaboration actually, and yeah, it's always really fruitful and nice collaboration. Laurits Tompkins is, for example, a former student of mine, also did great work on the IRS-13 area. Yeah, Andreas Eckert is an expert, I would say, regarding galactic center, galactic center studies. So he was actually together with Reinhard Genzel, who got the Nobel Prize a few years ago.
Oh, yeah.
The first person who looked at the direct vicinity of Sagittarius A star and identified single stars actually close to the supermassive black hole. So this is really outstanding work what they did. Lucas Labadie is the professor of my work group, where I'm working right now.
Cool.
Vladimir Karas is head of the Astronomical Institute in Prague, in the Czech Republic. Also close collaborator, and we are in close contact. Nadine Zabha, so she's now in Innsbruck located, and she was also former student of our work group, and is now working on METIS for the ELT.
Oh, cool.
Yeah, just really nice things ahead of us.
Yes.
And yeah, Lukas Steiniger is also a former student of our work group who contributed one figure to the paper. And Maria Melamed is my PhD student. Actually.
Cool.
So she started, I think, 2 weeks ago. And yeah, we're doing many cool stuff.
Very good.
Yeah. So the paper itself is describing a region in the galactic center. So first of all, for those who are not familiar with this environment, so if we zoom in towards the galactic center, at some point we are reaching the direct vicinity of Sagittarius A star, and with that I mean the so-called inner parsec. So where many different interesting sub-regions are located. So it's more like I would say, a puzzle. So the inner parsec. So there are different clusters, different interesting stars. So,
Mhm.
and one of these puzzles or pieces of puzzle is Iris 13. So, and historically, so this was identified as one star. So with like low resolution. So people just saw, okay, well, there is like one object, and then they donated it with some name. I think Iris 2 or 13.
Yeah.
So it was 30 years, 40 years ago. So, but anyhow, and so with higher resolution, people identified single objects in there or individual objects, and they saw that this is more or less a cluster of different objects.
Okay.
And based on narco observations that were carried out like around 20 years ago, we then know that actually the core of that cluster, so this is an embedded cluster with a lot of gas and dust, consists of Wolf-Rayet stars, massive Wolf-Rayet stars.
Okay.
So which was actually by itself already interesting, because Wolf-Rayet stars are interesting, I would say.
I think
And
so.
shortly after that, people, of course, raised the question, where is this object or where is this cluster coming from?
Yeah.
So, and I think this is actually a quite interesting question that one can raise and ask. And this is also a little bit the motivation for this paper here, so that we are looking in detail on individual objects and trying to disentangle a little bit the chaos, which we find quite often in the inner parsec.
Yeah.
Right. So this is more or less the same story that we have for the S cluster, which is also like a swarm of bees. These individual objects orbit Sagittarius A star on really fast orbits. And here, these objects of Iris 13 are a little bit slower, I would say,
Okay.
compared velocity-wise.
Yeah.
Still, the presence is, it's highly interesting.
Very.
So, and if we are looking at that cluster, then we find, from a photometric point of view, many different objects in different bands. Yeah, so H band, K band, L band, M band.
Okay.
Yeah, so this itself, I mean, this is already hinting to something, because we find in the inner parsec some objects that are a little bit, how to describe that? They are a little bit challenging to describe.
Okay.
Yeah? So there has been a debate a little bit about the nature of these objects.
Okay.
So, and maybe I have to here explain a little bit the broader context.
Okay.
Because in 2012 there was a finding of Stefan Gillissen from Garching, Max Planck Institute. And what the authors found was, or what they proposed was, that there is a gas cloud approaching Sagittarius A star.
Okay.
So, and then they proposed that this is maybe that this gas cloud could be flare up or increase the flaring activity of Sagittarius A star.
Okay.
Right? So, and then many scientists around the world observed that object, and what they have found was basically nothing. So no increased flaring activity. So the flux was more or less the same as before.
Yeah.
Right.
Yeah. Okay.
So and then, of course, or already at that point, some authors raised also the question about the nature of that source, and they proposed that this maybe is not a coreless cloud, but rather than a young stellar object, or maybe that there are at least some stellar counterpart hidden inside of the emission of that source.
Okay.
So this is maybe a little bit, this adds here a little bit to the discussion, because from a photometric point of view, the sources in Iris 13 are comparable to that object that has been found about over 10 years ago. Right? So this is always the thing that is connected to these objects. So what are these objects? Luckily, we are now in the situation that we have a huge database line that covers the galactic center. So actually, most of the observations that I'm analyzing here are already, I mean, these are archival data. So this is data that everybody can download. So which I find really amazing. So because the database line is so large, we can apply this really intense analysis
Yes.
to about these objects.
Cool.
So and we can monitor these objects over this long period. And I think this is really a unique thing to say about the galactic center or science in the galactic center, because we have this intense monitoring in different wave bands,
Right.
and then we can actually, again, target puzzle pieces.
Yes.
So this is, I think this is phenomenal, and especially compared to other regions. I mentioned that I'm also observing or working on galactic clusters, and sometimes you have the problem that you can derive proper motion, for example, for individual objects, because you have just one observation. But here we don't have this problem. We can do really like an in-detail analysis of these objects.
Mm-hmm. Cool. Very good.
Yeah.
I'm with you.
Yeah. So at some point I investigated a really interesting source, and the tools that I used, that I applied for this interesting source, so which is turned out to be a high mass young stellar object. These tools I used for the Iris 13 cluster. So this is basically what I'm doing here, is a multi-wavelength analysis, combining long data baselines to derive proper motions.
Cool.
But also apply a
Very
photometric analysis. And from this photometric analysis, I then go to the radiative transfer model that I apply, and to derive some properties, to get some information about these individual objects, and a better knowledge about the whole cluster region, how this region fits into this puzzle of the galactic center.
I'm with you. Very cool.
So so this is basically what we're doing here, always keeping in mind that that the nature of these objects is still under debate, right? But still, I think here it is helpful to broaden a little bit the view from a photometric point of view.
Very good.
So, and as I said, since most of the data is archival data, I mean, this is actually beneficial for this analysis, because so I more or less expanded a little bit my approach from the infrared regime also to the radio and sub regime, because here we see now Symphony NACO, for example, at 2.1. So we're describing a little bit the instruments, right? So Symphony is an amazing instrument mounted at a very large telescope like NACO.
Okay.
So, and NACO is more an imager, and Symphony also has an inbuilt IFU. So we can look at spectra related to individual pixel, right? So, and so these are basically these standard approaches that I'm more or less describing here, that we're applying, so we have our own built pipelines, but also we are using for comparison also the ESO pipelines.
Oh, good. Okay.
Okay. So of course, if you're using that many instruments, this is always connected to some challenges, right? So Symphony, for example, has an spatial pixel size of 12.5 milliarc seconds, and sometimes the L-band NACO data, for example, comes in with 13 milliarc seconds or 27 milliarc seconds. So this is then sometimes hard to target, but I mean, there are tools and ways to do that. So, but this is always something that it's not a fast approach here, but
good. So we got that data, and then we got some ALMA data we're throwing in there.
Exactly. So this ALMA data, actually, this was quite nice, because here I'm collaborating also with some colleagues from Japan, Masato Tsuboi. So I contacted him at some point and just said, hey, hello, I'm Florian. I'm working in the Galactic Center. You are also working there. So can we maybe share data? So, and then he agreed, actually. And so he sent me ALMA data, and really nicely reduced ALMA data. So that actually helped me here in this case, right? So he also published many articles using that
Yes.
same data. So sometimes we have then overlapping results, which is actually quite nice because I can always make a cross-checking. So what I'm doing, but also Lydia Moser, which is in here, named here in this section. She is also, or she was a former student of our work group, and she also worked on ALMA data. So, and with some publications, she made many reduced data public. Again, this is a little bit this approach using more public data, because there is a tendency sometimes that people are saying, yeah, it has to be really new, right? But sometimes it's also good to see what we have.
Yes,
right? And
I agree.
yeah.
Oh.
So anyhow, so with this huge data baseline that I now several times mentioned, I'm here now coming to this photometric analysis part, where I use the different calibrator stars, right, in order to use the radiative transfer model Hyperion.
Okay.
So Hyperion is a really nice radiative transfer model. So it was published like over 10 years ago. So open access, and so it uses basically single individual grains as emitters, right? So which is like highly it consumes a lot of power. And depending, of course, how many particles or dust particles you're using.
Okay.
So, but the very start is more like a really basic start. Here I have this magnitude equation, which is, I mean, well known, I think. So we have a reference star, and then in best case scenario, it's already a de-reddened reference star. But since this is the galactic center was observed so often, we can here be for sure. However, what I'm nowadays trying to do is using different calibrator stars from different sources, literature sources, and then look into my data and derive their calibration or calibration magnitudes, I would say. So to verify more or less that my approach is valid. So the basic start is I use the data, then I derive the hopefully matching magnitude of the calibrator stars, and then I use these calibrator stars to analyze the individual sources. It's a little bit, I would say, painful sometimes, but with this, I can be really sure that this approach is valid.
Good.
So here again, I mean, this is like the basic equations, well known. So here on the left, so we see table 1. So where I more or less indicate the number of photons or emitters and absorbers, right? So I did that there because one can actually use much higher numbers, but this is sometimes so time demanding. And then so especially during the pandemic, so when I stayed at home and I was working all the time, this was like a 24/7 cycle of all the time, because the number of photons was so high that I'm like, during the night I woke up, then restarted the simulations, and then went back to bed.
Oh yeah, sure, yeah, because clusters.
So this was just like really intense time. I mean, luckily I was awake because of my daughter. I took her milk, and then I was awake, and then I said, yeah, well, then I can just restart the
Oh well, she should be a co-author.
Yeah. Actually, she is. So in the acknowledgement, but anyhow,
very good.
So here on the right we see a sketch, and so this sketch is the basic idea.
Last one. Yep.
Yeah. So this sketch is the basic idea how we approach these sources, right? So this is a sketch of an class 1 young stellar object, which is then also implemented in the Hyperion radiative transfer model. And I liked the idea of that sketch. So this is, as it also stated in the caption, inspired by Cecilia Aguilar et al. 2016. And what is shown here in the middle is like a really young young protostar so indicated in red. And in this picture, we say, okay, well, so this emission can be seen in the H and K band as a faint emission because it's still really young, right?
Shrouded.
So, but then we have some sort of like pinkish envelope, which represents here the accretion disk, which actually we cannot see directly. And then, of course, we have then on larger distances dust at different sizes, right? So for example, the mid-infrared dust we can see in the LMM band in this with this approach here, this multi-wavelength approach. So, and this shields more or less the inner dust regions of the envelope.
Right.
Yeah, so there actually, because it's then shielded from radiation, and this dust then, of course, because it's shielded, is then can be seen in a submillimeter radio regime. Yeah, so here, for example, I indicate H30 alpha, but also other tracers are possible. So this is what we are seeing here is actually describes this multi-instrument approach, because H and K band we see with symphony, with NACO, yeah, and also the mid-infrared, but the submillimeter radio regime we see, for example, just with ALMA.
Yes.
So
very good.
This is, I think it's so this is more or less the idea. So we will come back to this later a little bit, why this is justified, right? Because I mean, of course, if we're approaching any given source with a more or less biased view, I mean, then of course we can do anything with it, right? So, but I mean, again, I mean, there are some justifications, but we will come to this later.
Okay.
Yeah. So this here is then followed by this high-pass filter that I here just briefly explain, because I like this because it applying such simple tools to the data is often then, I mean, it's free, right? I mean, here, I mean, imagine just the data, like imaging data, and then you apply a smoothing kernel, a Gaussian kernel to it, and then you subtract it from the original data. So that's it, basically. And then you get directly, so I mean, this is a well-known process and or a tool, but it gives you more information, I would say, about the data and what you're looking at. Yeah, so this is
good.
But yeah, this is more or less a story about this section here, but nothing more. But yeah, it helps. It helps.
Yeah, absolutely. Okay.
Yeah. Here I did actually a comparison. So in figure 2, so where I compared to the same data set, but with and without a filter, right? So on the left, we see actually a distance measurement of individual sources with respect to Sagittarius A star. So what I'm doing here is I'm fitting a Gaussian to individual sources, right? And then I just plot here the distance to Sagittarius A star. And this line here more or less indicates that there are no deviations. There is no really big spread or so, that the position is consistent whenever we are applying there and filter to it, right? So and then on the right side, actually, this is also quite nice. Here I did a measurement of the flux of these individual sources that I'm fitting. I should have represented here this in a logarithmic scaling, because these small bumps on the
ones down here, right?
I mean, barely nobody can see them. And then it was just later when it was accepted, and then I said, yeah, well, I mean, if anybody is interested, still they can send me an email or so. Yeah, so this is actually also makes sense, because the bluish bar here represents these non-filtered data, right? So also including here filaments, yeah. So and then these filaments, sometimes they are also like embedded objects. So but with this filter, actually we can actually disentangle these filaments. They consist of individual sources. That's the reason why we have here a little lower number for the high-pass filter objects, because in the bluer we see just like this one structure, but then more or less with this high-pass filter, it's kind of like falling apart. Of course, here one has to be a little bit careful, because one can also create point sources out of filaments. But that's actually a big advantage here in the galactic center, because I know I'm advertising this multi-wavelength approach, but we can also all the time cross-check here in different bands about the consistency.
Yes.
Because here I use just the L band, but yeah, so this, no, actually I see it's the K band, but anyhow, it doesn't change anything about my statement. So this is something that we still can then use the H band, right? So, and then sometimes also you have close by stars with overlapping PSF wings, right? And then with subtracting that, then you get then individual sources.
Okay.
So,
in fact, I think we got some image of that here. Finding chart.
So this is now on the left side, we see parts of the inner parsec. So this puzzle that I'm describing. So we see there actually quite nice regions: Sagittarius star, the supermassive black hole, Iris 16 cluster, IS7. We can actually see Iris 3, this embedded source on the top. So one can actually see a little bit there that there is an kind of like a bow shock around it. So it's still not clear. It's still not clear how this massive star or it can develop a bow shock, or what the source of that bow shock is. Because, I mean, we don't find a pretty high proper motion. So some people argue that maybe there is some sort of outflow connected to that creates the bow shock of RS3. Anyhow, we have to see. So I think future observations will disentangle that.
Cool.
Mystery. And here in the blue box, we see Iris 13 in the more or less original or traditional description. Because if we are looking at that region, the first time I looked at that, I thought to my supervisor, which was like a long time ago, I said, yeah, well, but the lower part also is connected to the upper part, right? And then she said, no, it's just the upper part. And I said, well, but to me, it looks connected. Yeah, well, no, it's just the upper part. So this is, for now, the reason why I put this box around this upper part. So we see there really bright core in it. So it's like really bright, so we cannot actually not see individual sources, which is because of the contrast, right? So, but, and also on top of this bright core, we see kind of like an arm, right? And this arm on the top of the bright source. Yeah, exactly. There are objects in it, and I think in 2004 or 5, it was already proposed that these objects might be candidate young stellar objects. So this was just an idea. At this time, the authors, which I think it was Andreas Eckert, who proposed that. And at this time, of course, the authors didn't have this long database line and was limited more or less to certain bands. So without the ALMA observations, for example. But I think it was still an interesting idea based on their photometric approach that they proposed. Because if you look at different bands at them, then you will see that the photometric behavior is different compared to main sequence stars, right? So there must be an explanation for that. So yeah. So and on the right side of that figure, this is now a zoomed-in view. Here is now the applied high-pass filter or smooth subtract algorithm. Right. And so the core of this, so you see on the right side alpha, beta, iota, epsilon, and so on and so forth. These are the Greek sources. So these sources, because they are really bright, they were discovered in the beginning. So in all the, or not all, but most of the other sources that are there labeled are newly detected sources. Right? Not all of them have near-infrared counterparts, but most of them. And we can actually observe these objects over a really long time, or many epochs. Cool. So this is actually pretty interesting. Some of them, disappear at some point, but I mean, this is something. So this view actually I saw for many months on a daily basis, day in and day out, to really pinpoint to individual sources that I was investigating and comparing this to K band, also H band. So this was like really, so this, I saw this way too often, I would say. But
it's still beautiful, still very nice.
Thank you. No, but this was like really, really intense. And these sources, here is now an L-band view, but they can, most of them, the majority can be detected also in the near infrared.
Okay.
Yeah. And parts of them also in ALMA.
Wow, that is really awesome. Very cool. Very good.
Yeah.
Okay. Onwards to results. What did you get?
Yeah. Here more or less, then we're using actually these individual sources and do here an HK and L band investigation analysis, mainly because of the upcoming color diagram, but also because of the limitation in the M band. So we don't have that many observations in the M band, and I wanted to be a little bit more consistent with the magnitudes, right? So I mean, I could have implemented it here, but still, in the end, it's I don't know. This was not the main target here.
Magnitudes here.
Yeah, I mean, this is more or less than counting individual counts. So the intensity, and then comparing it with our reference or the calibrator objects, and from that we derive the H band. So these are all dereddened values.
Yes.
Yeah, I think this is. I mean, it consumed many resources, this table. I remember how I did that, and this was, but still, the uncertainties connected to these magnitudes, these are pretty much standard. So whenever you're doing a photometric analysis in the galactic center, you get these values, and especially regarding these objects. So this is nothing that there have been other publications that also show similar magnitudes. And this is also what I mentioned in the beginning, that if we're comparing these objects here with other regions in the galactic center, so we find kind of like matching properties. So there are really just a few sources that really stands out from the crowd, I would say. So the other paper that I have that was published a few months ago of me, this, for example, targeted one particular object that really stands out of the crowd.
Okay, cool. I'm with you. Okay, the photometric analysis, proper motion.
Yeah, proper motions. I mean, this is here then also pretty much standard. So we are applying here an Gaussian fit to the data, and then we have the epoch or the time difference, and then we can
from the baseline
derive.
Okay.
Yeah, and then from that, actually, we can actually use these. I mean, so far fitting a Gaussian to the data. This is pretty much standard, but we can. What's interesting is actually what we can get from these proper motions. So, for example, one particular thing is we can calculate the velocity dispersion. Of the cluster. And this is actually, I think, a pretty much more interesting result that we can calculate actually the mass of based on the velocity dispersion that is needed, more or less, that the cluster itself stays in this compact shape that we observe, right? Because of course we can always ask, so why do we see such a compact and dense object in the galactic center? So it could have been evaporated, right? So all these sources could have been just like gone in different directions. And that's the reason why for some time some authors argued that there might be an intermediate mass black hole in it. And this is I mean, they proposed that. But and it's more or less an interesting idea.
It is.
But whenever people are investigating the kinematics of this cluster or looking at different tracers, possible tracers for an EMBH, they get more or less the same value, mass value.
Okay. Okay.
And this is actually
I like that.
highly consistent with the mass that I get here from the velocity dispersion
Yes.
that is calculated based on individual objects.
Cool.
Yeah. So this is, I think, this is quite exciting.
Yeah. Very good to get those dispersions. That's fantastic.
Yeah.
Okay. And let's
Yeah.
take a look at some of these color.
Yeah.
No, where we're at. We're still in proper motion. Okay.
Yeah. This is still proper motion here. I would say people could see here some trend in it. Like, so I have these 4 quadrants, right? A, B, C, D. And people could argue that maybe like a higher portion of objects are in quadrant B or
Yeah.
so, but it's not so, I would say the significance is not so high. So
Right.
in the end, I did not actually include here a statement about some direction that I see. So because still, even though I have this long database line, one should consider that this data will be updated in the future with upcoming observations with the ELT or other instruments like IRIS or so. And then, of course, I expect that we find an even higher number of objects in there, especially because it's so dense. Yeah. So, I mean, I cannot exclude that there are some blended sources or like, I don't know.
It's crowded field.
So that's the reason why I took here a little bit more careful approach and didn't state an cluster direction or a global direction of the cluster.
Okay.
Yeah.
Okay.
So on the right, so here we see more or less that the sources, if we are using the geometrical center of the individual sources of iris 13, then more or less we see here in Gaussian shape around the geometrical center. And so this was more or less the idea was here that if we are assuming that there is a geometrical center, then we have kind of like a smooth distribution of sources around that center, right? So this is more or less the idea of that figure. But
cool.
Yeah.
Good. Okay. Talk about the sources.
Yeah, because here in equation 5, I use the an isotropic parameter, right? So which uses the proper motion. So when we are looking at iris 13, one could, for example, think that there is no that this is a randomized distribution or there is no special arrangement of that source of these sources. So, and here actually I wanted to investigate with this anisotropic parameter if this holds. If we are seeing here an isotropic distribution, which is maybe implied also through that figure 5 that we have just talked about.
Yep.
Or if there are some hidden structures in it.
Yes.
Yeah. So this is more or less the approach that I used, which is actually well-known approach. Also, I mean, Gensel, for example, introduced that approach also for the inner parsec for many individual objects there, and so I adapted that more or less here.
Good. I'm with you. I got it. Okay.
Okay.
So we talked about ATD. And what we got here? Looks like we have, here's the anisotropic parameter.
Yeah. So what I did here was, so I disentangled a little bit the sources, because the E stars, I donate them as E stars, so E2, E3, and so on and so forth. They are considered to be main sequence stars. So I mentioned the Wolf-Rayet stars, but there's also an O supergiant in it. So that's the reason why I classified already here a little bit the content, the cluster members. So on the left we see the E stars, but I would say even though we see here that the anisotropic parameter peaks at 1 and -1 for the bin, 1 and -1.
Yes.
But still, I think that the significance is quite low, right? So that's the reason here. I mean, I just implemented this here to distinguish a little bit the distribution of these objects. On the right, however, you see that the dusty sources
Ooh,
are a little bit more distributed widely over all bins that are used there.
right.
Yeah.
Right.
So, but if you
Okay.
calculate actually the bin density of these sources, we can see actually if we are looking at all the sources. So on the lower left we have the dusty sources and the E
Yeah.
stars, right? So
Mhm.
together. But if we are now normalizing this distribution to the highest amount of sources in one bin,
Okay.
then we find the normalized number of sources on the right side. So here actually,
Okay.
so this is again the same representation more or less as we see on the left side, but more like from a, I would say, side view. Yeah, so it's more like a bar plot. We see actually that if we are normalizing that distribution, we see a peak at 1 and -1.
Yes.
So, and why is this important? So we can now look at uniform clusters, for example. We have here an example, for example. So this is one uniform cluster here, but I think it's a little bit, yeah, I would say the statement becomes clearer if we are looking at figure 7.
Let's go to figures.
Because there I implemented the Monte Carlo simulations of a non-uniform cluster. And what you see here is that also in agreement with other approaches of this problem is that if we are looking at an isotropic or non-uniform or anisotropic cluster, we see peaks at like the peaks at -1 and 1. Right?
Yes.
And this is exactly what we're seeing in figure 6 for the distribution of these objects.
Yes.
Yeah. So, and I think this is a really strong argument already that shows that we have here an anisotropic cluster, right? So, which is quite nice, I would say. So,
very good.
And also, I mean, why are we doing this? Because we want to show, this is the motivation, that it has a non-randomized distribution. Right.
Right.
So this is the main. So summarizing all the figures that we are looking that we have looked at is actually that we want to show that we have a non-randomized distribution, stellar distribution, which is actually found for many of these indicated puzzles that I mentioned in the beginning, right?
Yes.
So when we're looking at different regions, we often find that the arrangement of stellar objects, no matter if they are pre-main sequence stars or main sequence stars, they are not randomized. So this is the important takeaway message here.
Yes.
Yeah.
Yes.
So because the next question would be, why are they not randomized? But I will we can talk about this maybe at some other figure, but still this is I think it's a nice approach because I mean we have there a supermassive black hole, right? And we can of course ask, is there maybe an imprint that we can observe for individual objects or regions of that supermassive black hole on these objects or regions? Yeah. So this here already suggesting that we do see an imprint.
Correct. Good. Cool. That is very nice.
Yeah.
Very, very nice. Okay. Ooh, double factorials. Ooh, awesome.
Yeah. No, we don't have to disentangle this chaotic equation.
It's a probability distribution function.
Yeah.
Okay. Photometric analysis. Ooh, here we go. Ooh,
yeah. So this is again this multi-wavelength analysis.
Okay.
I'm not sure why I excluded here the L band, so at 3.8 microns or 3.7, but we see here on the left the H band at 1.6 microns, then the K band at 2.1 microns, and then the M band at 4.5 microns. I think I left the L band out of the picture because I already showed an L band overview in the beginning of the publication.
Correct.
Yeah. So what I'm doing here is I'm focusing a little bit on these Greek sources that are in the center of the upper part of the cluster. So you can see that at 4.5 microns, actually, that these are really sticking out a little bit also compared to other objects. Of course, I have to always in these figures balance a little bit between contrast and what to show, not to show in too high contrast or not. So that's the reason why some of these other additional objects seem to be not present there. But this is just one representation, and I think we also published a lot of material along this publication here, so where people can see that actually. Anyhow, so we see here that consistently we can see these Greek sources in all the M bands. Of course, in the H band it's a little bit harder. Again, here is the contrast that is targeting, or it's not contributing a little bit to the story. But anyhow, I mean, I think it's quite nice that we have this multi-wavelength detection of these sources.
Yes, very cool.
Yeah.
Here's our photometric, and here's our baseline 2002 to 2018.
Yeah.
Beautiful.
Yeah, here what I'm doing here again, so is to compare filtered and non-filtered data. Yeah, so I picked here, I picked here now one particular object. So randomly I started with just the source one, so DS1.
Yes.
Yeah. So then I derived here more or less the magnitude for every epoch. And then I went, or I got the results. So down the average and the median, which is more or less consistent with each other, and just inside of the uncertainties. I think this is also
solid,
showing that whenever you're using a filter, of course, one have to still compare a little bit, but it's still trustworthy that one can
over the whole baseline. Over the whole baseline.
Yeah, exactly.
That's
so this is I think this is important here. So I think if we just would focus on one epoch, then of course this would be a little bit tricky, because we couldn't then really justify that, or that there could be an outlier or whatever. But here we see actually, so we don't expect many variations of the magnitude, right?
They're not flaring or blowing up or something like that.
No. Fortunately not.
Then we got D-red.
So this is here now. This is now. This was a really long road. So this was really intense to derive this. I mean, actually, I started with that here, right? So here I also included the M band, because here I was focusing on these Greek named objects, right, which are really prominent in the M band, but also in longer wavelength. We will see that in a few slides, pages. But so here, I used different calibrator stars and compared also these results of the literature with known magnitudes, and more or less everything is consistent here. So I think this is also a nice result to show that these are not coreless objects, but that they have a near-infrared. Because if we assume I mean, to every band there's a temperature connected, right? So H and K band, several thousand to tens thousands of Kelvin, but also the L band is then quite cold, and it gets colder to the M band, and so on and so forth, right? So if we expect that these objects would be coreless objects, we wouldn't be able to observe them in the K and H band, because they would be just destroyed.
Yep, very good. Okay. Onward, stellar content. Here we go. ISOs.
Exactly. So this is now more or less the justification why we are applying here the Hyperion radiative transfer model, assuming that these are young stellar objects. So we have, for example, here this lime-colored or green-colored X3 point. So this is then public. So this data point is based on a publication that was published around, I think, 6 or 7 months ago. So where I investigated an object in detail, also over the same database line, and with this, actually, this was more or less the starting point also for this classification here. I implemented many different sources and cross-checked more or less this upper part, because this was actually stated in this publication that I mentioned in 2004, that the objects, these Greek named objects, are the young stellar objects. So they are also shown in here as dusty objects. Yeah. So, and yeah, they show an expected, I would say, magnitude. And here I just classified the dusty or the DS source into two groups. The first group is actually the group that I say, okay, well, we can say for sure that they show an color position that is consistent for young stellar objects or candidate young stellar objects.
Okay.
And whereas we have also other parts of this cluster sample that is consistent with evolved stars. So that's the reason why I put in here Iris 3, for example. If you recall this bright source of this bow shock, right? So which I showed in the L band in the beginning.
Yes.
One could, for example, argue critically that these dusty objects are not so special because they are just embedded sources as many other sources in a parsec. However, if we are using, or if we are looking at the most prominent embedded source, Iris 3, we see actually that it's below this black body linear line there that I implemented here, right? So one could also describe this as a one component black body line, right? So what we expect is actually for all these sources which are below that line or on that line is that they just have one component, a stellar component, whereas all these other sources have different components. Yeah, so also an envelope. So that's the reason why they are up there more or less.
Gotcha. Yes.
Yeah. So because the envelope blocks a lot of the K-band emission, right? So that's the reason why we have here different positions in this diagram. Yeah.
Gotcha.
So this was already established in 1998 by Ishii, but I think it's still interesting that one can, with these simple tools, already find these interesting sources.
Yeah. Very nice. Good. Okay. Color. Ooh.
So this is now again so if you recall this bluish box in the beginning in the L band, more or less it's the same region but observed in CO, at 343 gigahertz with ALMA. So we see here in the middle this brightish blob, which is not their labels, but still this is the cluster core, or supposed to be the cluster core. And here we see actually why we are emphasizing a little bit the analysis of these dusty objects. Yeah, because we can here see clearly that they show a submillimeter radio counterpart. So, and if we are now thinking about figure 1. So where we think about this this picture about this shielded dust component, right? So so that's actually something that here contributes. So here it makes sense actually that despite we have such an high outflow of these Wolf-Rayet stars, because Wolf-Rayet stars show like velocities of 2,000 kilometers per second or whatnot. So we expect there high radiation actually. So CO or other material would have been probably destroyed if we don't shield these dust grains, right? But if we are assuming here that there are embedded sources, not one component, but embedded sources with an envelope that shields the inner parts of the envelope, then it makes sense that we are observing here these counterparts at the position of the mid-infrared and near-infrared emission of these sources. Right? So a long sentence, but but here this multi-wavelength ansatz, this makes here sense actually if we're approaching these regions with these long database lines with different wavelength regimes.
Okay. All right. I'm with you. Okay. Good. Okay. ALMA. And
so here is now the outcome of the radiative transfer model, and these are best fit SEDs, of course. What to say about these? This was like really long road, really painful and long. So because there is an easy approach to that. So if you if you use a tool or code as Hyperion, you have like so many different parameters and everything. So at some point, the authors or the guy who coded it, Robitaille was it? So he actually published many pre-calculated SEDs. However, I think it's a little bit, or I choose a more individual approach here.
Yeah.
So I defined, based on this photometric analysis, an own spectrum. What you can see here in these orange data points. So they are representing the flux that are derived from the photometric analysis. Yeah.
Yes.
So this is more or less the input that I gave to the code. Yeah. And then I adjusted the code or the parameters to derive these SEDs. So most of the time, I think this was nice, and I got a nice result from many sources. So we have here eta, which was a little bit hard because I was not able to really, it was connected with many difficulties for eta. So that's the reason why we think that maybe eta is not a class 1 Young-Celler object.
Yeah, it could be small.
But here, because it's not directly following this pattern, I was not able to find any or a satisfying parameter setup that represents the emission. However, so I discussed this later on, but so regarding these SEDs, I think it's important to emphasize that this longer wavelengths here are a key for this analysis, because most of the time, if we are close to Sagittarius star, we are limited to the near infrared and the mid infrared.
Yes.
Yeah? But Sagittarius star is a radio source, which was first observed in the radio regime. So that's the reason why, when we are looking at Sagittarius star, with ALMA, for example, we just see like a really, really bright blob, which blocks everything inside of the S cluster. However, we are here about 0.1 parsec away from Sagittarius star, and therefore we have access to these wavelength regimes. So, and when we now look at these sources, we can actually verify this approach of this Young-Celler object model.
Yes.
Yeah, by incorporating these longer wavelengths.
Yeah.
Yeah. So cool. This is here really key to it, and also shows a little bit the limitations if you go closer to Sagittarius star. And that's the reason why this publication, I would say, of course, I wrote it, but I think it's really important.
It's great. It's great. It's good. It's important.
No, but more or less to classify a little bit also these
anchor
objects
out there is really nice, right? At the longer wavelength, that's a key anchor point.
Exactly. So this makes really a difference, and I think this helps also to understand a little bit the nature of these sources.
Yeah. Cool. Yeah. That's our SEDs and
the parameters that I used, right? So I did, I mean, endless fits, but here I more or less for the shown SED in figure 11, I implemented 3 SED solutions. So low, then best fit, and then high. So this is more or less here then the shows or is represented here by this plus minus in table 8, so that there are actually 3 SEDs included.
Got it. Okay.
Yeah.
Okay.
It is more or less. What's interesting here is that, so I mentioned this other publication I had like a few months ago, and what I found for this publication was that the flux distribution of that object is consistent with a high mass Young-Celler object. So the interesting part here now is that if we are looking at the mass of table 8, so we see that most of the sources are indeed also high mass objects. Not all, but like intermediate also, we have also some low mass, but the tendency is there that there are at least some high mass objects.
Got it.
Which is interesting if we are thinking about these 4 stars, which are also high mass stars in the Iris 13 cluster. So the Iris 13 cluster shows like a really high core density mass. Yeah. So this is contributing a little bit to this classification of that source of that region. Yeah.
Right. Yeah. Okay. Very interesting.
Yeah. I think this is a really great result. Of course, I'm saying
Yeah.
this, but still,
Okay.
thinking about that region, it's. I mean, I wouldn't say
Okay.
it's a big surprise, but still,
Oh,
it adds a little bit up to already established measurements and observations.
okay. I like that table. Very cool.
Yeah.
Okay, 8, and we shall take a look at J-band.
Yeah, J-band. So this is, I mean, the noisy J-band. So I think there is only one epoch. So where people observe the galactic center in J-band. So I think you get an idea why people rarely observe the galactic center in J-band. But it's, I mean, but still, it's great because I see we can find or re-identify their eta. Yeah, of course, here again, I balanced a little bit the contrast here, but still, the low mass object eta here can be seen in J-band, because there I can then use J-band magnitudes actually for the classification of eta.
Right.
Yeah. So this is actually something that during the referee process, the referee pointed out that this is actually consistent with an object, or this is actually class 1 object. I falsely say class 2, but it's a class 1 object. But you can directly get that from the original classification by LADA from 1987.
7 or so.
So where they actually showed this classification of different young stellar objects of different classes, and there they used the J-band. So eta is here actually the strongest proof actually for the presence of an Canadian young stellar object. So this is, I think, also nice, even though it's a low mass object, but still the presence of this object, is highly consistent with established theories and observations. Yeah.
Cool.
And here, figure 13, this was something that was, I included that to convince the referee, because the referee was questioning a little bit the biased approach of fitting a young stellar object model to the flux distribution that we had. Yeah. So what I used here was the observations for Iris 3. So you recall the Bow-Shock, right? This
the Bow-Shock.
Bright Bow-Shock, the Bow-Shock source in the beginning.
Yes.
Really nice. So these values here are more or less consistent with interferometric observations of that same object. Yeah. So the orange data points.
Okay.
However, if we are assuming here or a biased assumption that Iris 3 is an young stellar object, we end up with these SEDs. So the pinkish SED on the lower SED of Pot et al. 2008 shows actually the SED that we get if we include the established and derived properties of Iris 3.
Okay.
What you directly see is that this does not match the consistent data points, the fluxes, right? We have to artificially increase the temperature. I mean, look at the temperature. So the Iris 3 is classified as a cool carbon star, right? Cool carbon star. So with velocity, with temperatures of like, several thousand or whatever, like 3,000 Kelvin. However, we have to increase that here to like huge values in order to match the near-infrared and mid-infrared flux.
Barely.
However, we are not able to match here the ALMA or the radio submillimeter data point on the right.
Still off.
However, it shows actually that Hyperion is indeed not able to fit random flux distribution and tells you, well, this is a young stellar object, right?
Sure.
So this is like what we are doing here is like a really critical view on our own results, and I think it's a really nice result that we show that for main sequence stars or AGB stars, but but these or evolved stars, that Hyperion is indeed not able to reproduce
Okay.
with given temperatures
Right.
the flux distribution.
Right.
Yeah.
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 So we need something more in the order of a few hundred K.
Yeah. Yeah. Sure. Yeah.
15.
This
Ooh,
is
good
that's quite
size.
nice.
Very nice. Very cool. 13, 14, validity of the RS. And
Yeah.
we end up with
Here actually table 9 is a
Yeah.
really nice. I mean,
Yeah.
it looks a little bit innocent, I would say, table 9. But what it's proposing is that
Yeah.
if we are looking at the distribution of the objects, we find that most of the objects are in the tip region of the cluster. Right? So if we're looking at the cluster, so we have the core region, we have the tip region.
Yep.
Yeah. So
Yep.
most of these younger objects we find in the tip region, whereas we find the evolved objects in the core region.
Okay.
Yeah.
2 gens.
So that means if we consider that this is like an cluster where all, of course, we are considering that this is a cluster, but then we see actually two generations of stellar objects in there.
Yes.
So
That
they're
would be
distinguished by their age, of course, so because the second generation is less than 1 million years old, and the other one is then roughly a few million years old. So I wrote here 4, but this could be actually a little bit older or a bit younger. But anyhow, so it's not so important about the exact number, but still that we have here a difference of the stellar age.
Yes.
And of course, here we can speculate a little bit. Why is that so? So why do we have in the tip region younger objects, and in the core region we have older objects?
Yes. Yeah, that's a little unusual. You might expect the old ones out first, right?
Yeah. So we expect a little bit more, a more mixture or wide mixture. But I think this is a really nice result.
Beautiful.
Because it opens up many different scientific possibilities in classifying that object. So maybe we can, when we now come to the next figure, I think I already indicated this here in figure 14. So here in figure 14, you see the solving part with a question mark.
Right.
In the tip. So just briefly, let me explain to you what we see here. So the line contours are based on symphony observations of that region and represent forbidden iron line. Yeah.
Okay. Good.
Forbidden iron line at certain velocity.
Gotcha.
And it reassembles the shape or the distribution of the dust. So we see here the highest amount. So we see in the core region, but also we see in the tip region some emission. And the lower part looks more like an dissolving part. That's the reason why we're putting there a question mark in it. So with 3 like prominent high mass stars. So Iris 2C is a foreground star. Iris 2L is maybe a cluster member, and Iris 2S is also maybe a cluster member. There have been observations of that region that actually support the idea that this whole region is connected. Because again, historically, people thought that just the center or the core region is the cluster. But there have been observations of the polarization angle, for example, that shows that this region is individual compared to the surrounding. So it sticks out a little bit. So you have like one polarization angle, and this already indicates that you have here like a connected region.
Yes, definitely. Cool.
Yeah. So I think this is like really nice result here, and also proposes a little bit a different perspective on that object. Which makes sense if we are looking at the literature and looking at different ideas that have been proposed already 20 years ago, that this is maybe a cluster that is like an infalling or inspiraling cluster, which was brought from outside of the inner parsec. Right? So I'm always talking about the inner parsec, right? But we have also a lot of material outside of the inner parsec.
Sure.
And there have been many theoretical and observational approaches to that region that investigated an interplay and possible interplay
Yes.
with the inner parsec and the outer parsec, so to
Yes.
say.
Russ.
And this cluster here is maybe a link of that outer region and the inner region. Yeah.
Okay. Cool.
So,
Nice. Nice. The stream. The stream.
yeah. Yeah.
Good. Oh, and then we got a figure 15 here, angular momentum. Whoa.
Yeah. So here, I mean, this is basically, I used the already results to show here that the majority of objects, are tend to be organized close to the counterclockwise disk. So I mentioned different kinematic structures in the inner parsec, right?
Yeah.
So already like many years ago, people found that some of the stars or their cluster sample is arranged in two individual disks. So the clockwise disk and the counterclockwise disk.
Okay.
So, and then one can of course investigate a little bit the membership of these disk structures. And this is basically what I'm doing here. I show that the majority of these objects are actually tend to or could be associated with this large kinematic structures.
Oh, most of them peak around -1.
Yeah, exactly. So here actually we see actually I didn't include any further figures because initially the paper was like 70 pages long, and then then the referee complained, and it's so that's the reason why I left some stuff out of there. But
on the cutting floor, yeah, it does happen. Okay.
Yeah.
Very good. And then finally we come to the final figure, which we have a spectrum.
Yes. So there is the MUST archive, right? So where at some point I always like scanning different archives, and then I found this near spec spectrum here, observed with James Webb Space Telescope, and I thought it's maybe an interesting outlook, more or less, for upcoming observations, because we see here a nice spectrum like this that ends roughly around the beginning mid-infrared regime. So we have left H-band or parts of the H-band, then in the middle K-band, and then on the right where the water ice absorption is located, so the beginning L-band. And what we see here are, so first of all, I mean, I think this is a nice spectrum of the galactic center. So it was a little bit hard to invest or to find the associated region, but I don't know if I implemented here the different field of views, because actually what happened in that observation was that the PI, or that the observations were carried out of different regions, and then it was stacked. So the imaging data cannot be used, but at least the spectrum can be recycled, I would say.
Fair enough.
And what's really nice is here that, for example, in the H-band, we are always limited by the telluric absorption and emission lines. So I have never seen such a nice Paschen alpha line.
Yeah.
So without any tellurics, I mean, this is just hell. It's like hell to model telluric absorption and emission lines. This is just like, because I always then avoid that region. But here I get like this really nice peak, also with a bracket delta and other lines, which is quite nice.
Very nice. Very cool.
And also what's interesting is that it has been proposed with VLT observations for I don't know, I forgot the instrument, but that there are water ice absorption features in the galactic center. And this is basically what we here show, is that this is consistent with already carried out observations of the galactic center.
Okay.
Yeah.
Good.
So many interesting lines, but we have to wait for more data, and then we can actually look at line maps of this.
LT.
So
there we go. Okay. Very cool.
And maybe here just a short addition here on equation 10 and 9. I calculate here speculatively and multiplicity and companion fraction. So assuming that there are
multiplicity. Okay. Yes, I'm with you.
Assuming that there are binaries in it. So I accentuate this a little bit, that I have found some sources show a little bit small variations, and then I
Binary
speculate
triple
there
quad.
might be
No binary
binaries. So
quad.
assuming
Yeah.
that, actually, I found
Okay.
really nice thing that these results out of this purely speculative approach is highly consistent with other galactic clusters, which are located somewhere else. Yeah. So this is the multiplicity fraction, and the companion fraction is consistent with comparable clusters, galactic clusters, actually. So this is, I think, also a nice result, but it was also implemented here for an outlook, right? Because there have been studies that suggested that there are more binaries in the galactic center, but this is a puzzling question. So because we don't know why we don't see that many binaries. You would expect much more, but we don't see them. So that's the reason why I included that here.
Very good. Yeah, because yes,
yeah,
that's a good avenue to continue investigating, I think.
Yeah.
Very cool. And we end up with some conclusions. And then there are a couple of really whopping appendices. I highly encourage people to check those out if you want to look at the most of the raw data and things like that. Do check those out. It's really, really cool. And I got to check this out since you mentioned it. The acknowledgements. There we go.
Yeah. So you see, if you scroll down, scroll down a little bit, then you see AP. AP is my daughter Aurelia.
Very good.
Contributed useful points to this. But actually, I talk about this with my children about them, and sometimes they have also ideas.
She's published, so that's great.
Yeah.
Florian, I want to thank you so much for walking us through this very awesome article. Very nice.
Yeah, you're welcome.
And you touched on it a couple of times during the talk or during the walking through the paper there. Of where do we go from here, given the published article? Is there are there other clusters around the galactic center that might be worth looking at? You mentioned additional data coming to wire out some of the stuff. You showed a preliminary spectrum. Maybe we get some spectrums of these things, and just sort of. And there's always more radiative transfer calculations one can do. But where do you think we go with this? So let's say over the next couple of years.
Yeah, I think this classification opens up many possibilities.
Okay.
And you have seen that the title already there is an 1 in it. So it's like
I noticed that.
There's a 1. So there's also like 2,
or
which
3.
is already yeah. Let's see. But there's actually, I mean, I already submitted the follow-up paper.
Okay.
Yeah. So this is I'm waiting for the referee report, but I think there are many different and interesting aspects connected to it if we are following that path and this classification. And I think there are still many unresolved mysteries and of the galactic center, how these young objects were like, I mean, how they ended up there so close to a supermassive black hole.
Right. That's just
I think
question.
on a larger perspective here, I think that one can use hopefully these results also to understand maybe other galactic cores and understand a little bit the emission or the processes. So I think, I mean, there will be more in the future, and also with upcoming observations, James Webb, but also IRIS, ELT, and so on and so forth, but also Gravity Plus is around the corner. And so I think there are many not challenges, but opportunities. Yeah, but also challenges.
Always. One comes with the other. Very cool. Well, I really look forward to seeing this field evolve over at least the next time scale for your next referee report, but also just the next couple of years. I think it's a very exciting topic of, star formation, very near black holes. So very cool. And they're young, very young. So it's very good. Cool. Florian, thank you so much.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.